Welcome to ICSE Masterclass. All right, let's get right into it. If you're gearing up for your physics exam, you know Chapter 1, Force, is a big one. It's filled with concepts that can seriously make or break your final score. So today, we're going to tackle it head-on and make sure you master it.
So, let's start with a question that I bet has crossed your mind. What is the deal with these meter rule problems? They look so simple on the surface, right? But year after year, they trip up so many students. Well, it's because there's this one sneaky little detail that's super easy to miss, but is absolutely crucial to getting the right answer.
You know, we're not just going to read from the textbook today. Nope, we're going a step further. We've actually gone through official examiner reports to pinpoint the exact places where students keep losing marks. The goal here is simple, to make sure you don't fall into the same traps.
Okay, first up, the turning effect of force. You probably know it as moment. This right here, this is the heart of the matter, the core idea behind every single one of those tricky meter rule questions.
See, the thing about moments is it's not just about how much muscle you put into it, how much force you apply. It's all about where you apply that force. And hey, here's a little pro tip for you, something to make your calculations way easier. Just remember to treat anti-clockwise moments as positive. Trust me, it'll keep all your work super consistent and clean.
Okay, so take a look at this. It's a classic exam problem, right? You've got a meter rule, a knife edge pivot, some weights hanging off it. Pretty standard stuff. But I want you to zoom in on two little words in the question. Uniform meter rule. It sounds so simple, but believe me, those two words are the absolute key to everything. So what's the big mistake? Well, according to the official CISE's analysis of student papers, the #1 error, and I mean by a long shot, is completely forgetting about the weight of the ruler itself. For a uniform meter rule, its own weight acts right at its center of gravity. And where is that? You got it, the 50-centimeter mark. It's like an invisible weight you have to account for.
So here's how you nail it every single time. Just follow these steps. First, find your pivot. Then add up all the anti-clockwise moments. Next, and this is the crucial part, calculate the clockwise moments, making sure you include the ruler's weight. Finally, you just apply the principle of moments. And just like that, what used to be a trap is now a guaranteed mark for you. Easy.
All right, so we've talked about forces that cause something to pivot. Now let's take that same idea and apply it to something that's always turning. We're talking about circular motion. And guess what? This is another one of those topics where a really common mix-up can cost you big time.
Okay, this is huge. You have to get this straight. Centripetal force is the real deal. It's the actual force pulling something towards the center, keeping it on that circular path. Think of the tension in a string when you're spinning a stone. Now, centrifugal force, that's not a real force. It's what's often called a fictitious force. It's that outward pull you feel, like on a merry-go-round. And that feeling is just your body's inertia trying to fly off in a straight line. It feels real, but it's an effect, not a cause.
And hey, don't just take it from me. The examiners themselves say it in their comments. They see this confusion between centripetal and centrifugal all the time. So getting this one distinction right, absolutely essential. It's a make-or-break concept.
So here's your exam day mantra. The force that's responsible for making something move in a circle is always the centripetal force. Period. If they ask you about a stone on a string, the planet orbiting the sun, a car turning a corner, the answer is centripetal force. That's the one doing the work.
Okay, let's move on and connect some dots. We're going to see how force ties into work, energy, and power. Now, these three are like a trio that always works together, and understanding how they're all linked is super, super important.
Now, you've probably heard this a million times. The law of conservation of energy. Energy can't be created or destroyed, just change from one form to another. So in a perfect, ideal world, the total mechanical energy, that's your potential plus your kinetic, stays the same. But, and this is a big but, you got to watch out for the bad guy in this story, friction.
Okay, this table right here, this is basically a cheat sheet for a really common type of exam question. Let's break it down. When something moves down in the same direction as gravity, like a car rolling down a hill, the work done by gravity is positive. Makes sense, right? Gravity's helping it along. But when you move up against gravity, like climbing a ladder, the work done is negative. You're fighting gravity. And here's the one that catches people. If you're just walking on a flat, level road, your vertical height isn't changing, so the work done by gravity is a big, fat zero.
Let's put this into practice with a classic sample paper problem. We've got a skateboarder, Richa, at the top of a ramp at point P. As she starts rolling down, what's happening? Well, all that stored up potential energy she has at the top is getting converted into kinetic energy, the energy of motion, as she reaches the bottom at point Q.
So, let's imagine for a second that this is a perfect frictionless world. In that case, all of her potential energy at the top, mgh, magically transforms into kinetic energy 1/2 mv squared at the bottom. The math here tells us that her kinetic energy at point Q would be 2,000 joules. It's a really straightforward application of the principle, a simple one-to-one conversion.
Aha! But here it is. Here's the trap. The problem tells us she loses 500 joules of energy to friction. And what does that mean? It means our perfect little law of conservation of mechanical energy doesn't apply anymore. That energy didn't just disappear, it was stolen by friction and turned into heat. Examiners love to see if you remember this. The real world has friction, and you have to subtract that energy loss.
Okay, let's bring it all home. I'm going to give you a super quick summary of the biggest takeaways, the things you absolutely have to remember to lock in those marks. All right, here they are, the top 3 exam traps to avoid. Number 1, the invisible weight. Please always remember to include the weight of that uniform meter rule acting at the 50 centimeter mark. Number 2, the real versus apparent force. Centripetal is the real force, pulling inwards. Centrifugal is just a feeling, an effect of inertia. And number 3, the energy thief. Mechanical energy is only conserved if there's no friction. Always check if that energy thief is in the problem.
And there you have it. That's your masterclass on the trickiest parts of the force chapter. If you can remember to avoid these common traps, you are going to be in fantastic shape. Thanks so much for watching. Now, I want to hear from you. What's the one concept from this chapter you want us to do a super deep dive on next? Drop it in the comments below.